All right. As folks are rolling in, I'd like to welcome everyone to today's rendition of the Third Coast Water Seminar Series. This is just kind of like a little list of all the seminars that we've run so far since restarting this program in 2025, as well as today's and future seminar series. So today, I hope you all are in the right place. We will be hearing from two folks from the Hampton Roads Sanitation District who will be talking about growing a regional innovation ecosystem. Just a little bit of background, the Third Coast Water Seminar Series. Um, was started up by Current and our partners several years ago during the pandemic, and we recently kind of re-upped the series as part of our Great Lakes Renew initiative, which I will get into more of what that means shortly. Speakers are selected based off of recommendations from partners within our R&D ecosystem and kind of focusing on the general theme of transforming waste into wealth, which is kind of the ethos behind the Great Lakes Renew Innovation Engine. So as promised, a little bit about Current. So Current is a Chicago-based nonprofit focused on sort of three core missions or three core goals. One is to grow the circular blue economy. The second is to accelerate water innovation, and the third is to solve pressing water challenges. So Current, as a nonprofit, is sort of the quarterbacking organization behind a multi-organization and multi-state effort called Great Lakes Renew. Great Lakes Renew is an innovation engine that's part of the inaugural class of NSF engines, initially awarded in 2024 with up to $160 million in funding over the course of 10 years. Um, Renew stands for the recovery of energy, nutrients, critical elements, and water. So those are sort of our key kind of categories that the Renew work is focused on. And we approach that from multiple different areas. So we're looking at spurring the circular economy transition. So looking at the workforce required to support circular economy innovation. We're supporting the invention and commercialization of selective separation technologies. So that is through funding of research and development projects at both like the academic level, as well as supporting startups and innovators in that space who are developing use-inspired technologies to support the circular economy. And then we're also supporting the attraction and retention of water-intensive industries in the region, so specifically the Great Lakes region, including Illinois, Indiana, Ohio, Michigan, Wisconsin, and Minnesota. So within that class of the recovery of nutrients, elements, and water, we are currently supporting several innovative research projects. So just to kind of give you a little bit of a highlight into some of those. So we are supporting projects in PFAS sensing, in critical mineral extraction, in nutrient extraction and recovery. And these are all through our research partners at various institutions. If you're interested in learning more about what Current does, about what Great Lakes Renew is, we encourage you to follow us on our socials. Then you can also take a quick scan of that QR code, and that'll lead you to Current's website. But without further ado, what you all came here for, I want to pass it over to two of our partners, Dr. Nancy Love and Dr. George Wells, who will be introducing our speakers for today. And just like a little bit of context, so the way the seminar works, we will have introductions, and then we will have a large portion of 30 to 40 minutes dedicated to our speakers to talk on their topic. And then we will have time for Q&A at the end. So feel free to, as the talk is going, to drop questions in the Q&A box, and we will get to those at the end. But without further ado, I'll pass it off to Nancy.
Okay, thanks, Tyler, and hello, everybody. Good afternoon or morning, depending on where you're coming in from. I'm really happy to introduce the first of our two speakers today. It's Jay Bernas, and so Jay is a licensed professional engineer. who has more than 30 years of experience in engineering, financial strategy, and utility management. He is currently the general manager and CEO of the Hampton Roads Sanitation District, which is the 14th largest wastewater utility in the United States, and I would argue among the most innovative. He leads a large workforce of dedicated wastewater professionals, and it's really a unique utility. I've seen this firsthand in terms of the way in which they work with their workforce, and what they call the people first philosophy is really very apparent with this utility. It's a wonderful place to visit and it's a wonderful place to work. I know, as I have former students there. Jay holds, again, in addition to his professional engineering license, he earned a master's in business administration from William and Mary, which is not far from Hampton Roads. And so Jay's going to be one of our speakers today, and I'll pass it now off to George, who's going to introduce the second speaker.
Thanks, Nancy. Very much a pleasure to introduce Charles Bott, our second speaker for the day. Charles is the Chief Technology Officer at HRSD. He's been at HRSD since 2009. And at HRSD, Charles manages technology innovation, research and development for their wastewater treatment plants and interceptor systems. And I'll just second Nancy in highlighting the fact that HRSD is certainly one of the, and probably the leading utility in terms of innovation and implementation of new approaches and new technologies. And it's been very much a pleasure over the last more than a decade or so to collaborate with Charles and other folks at HRSD and a variety of different projects. Charles is an adjunct professor in the departments of Civil and Environmental Engineering at Virginia Tech and at Old Dominion University, and also in the Department of Civil and Water Engineering at Université Laval in Quebec, Canada. He's a bachelor's degree in civil engineering from the Virginia Military Institute, a master's degree in environmental engineering from Johns Hopkins University, and a PhD in civil and environmental engineering from Virginia Tech. I believe working with Nancy, if I remember correctly. Charles has expertise in a whole range of different areas, from advanced water treatment technologies to nutrient removal and recovery, anammox processes, biological treatment, modeling and design, anaerobic processes, biogas conditioning, and the like. And I think we'll hear about some of those areas today. He also has a long list of awards and honors. I'll just highlight a couple. He's a fellow of the Water Environment Federation. Actually plays a very leading role, and it's been fun to interact with Charles through WEF for the last many years. He's a member of the Science and Technology Advisory Committee to the Chesapeake Bay Program Executive Council, and I believe you're still a member of the National Science Foundation Engineering Directorate Advisory Committee as well. So Charles and Jay, very much a pleasure to welcome you, and thank you for joining us, and we'll turn the floor over to you.
Well, great. Thank you. And thank you for those kind introductions. And thank you, Dr. Love, for your grad student. He just started this week. So we really appreciate our continued partnership with your university. Again, great to help. Glad to be invited to help tell our story about HRSD and this regional innovation ecosystem that we're building. So if you're not familiar with HRSD, we're a regional wastewater authority in Eastern Virginia. We serve 20 cities and counties, about 1.9 million people, which is over 20% of all Virginians. But our region's flat. So we have 14 wastewater plants of different sizes, 8 big plants, 6 smaller plants, all spread throughout Eastern Virginia. We have the capacity to treat 225 million gallons per day. And our 10-year CIP is $3.4 billion. So I think it's helpful to set the stage on what our big challenges are. So we have 2 big regulatory challenges. One is Clean Water Act compliance for SSOs. So we are not a CSO community, we're an SSO community. And the Chesapeake Bay restoration. The Chesapeake Bay is the largest estuary in the US, and it suffers from nutrient pollution. So we're continuing to ratchet down on the nutrients going to the Chesapeake Bay. And now we have PFAS, right? So all these big regulatory drivers, which is really pushing our CIP up over $3 billion. 68% of that is regulatory required. And the bottom line is rates are going up. And so one of the things as a utility leader that I've been pushing to my fellow utility leaders, innovation is the key to affordability. We are not going to be able to control our service area socioeconomic status But one of the things we can control is our operational cost, our capital costs. And we think that we can do that through innovation. And we have. And I'll talk about some of the things that we've been able to do. But first, I'll talk about our R&D group led by Dr. Bott. It's one of the largest in the country. We've got 23 staff, 6 PhDs, 7 PhDs in progress. We have 30 active water research foundation projects. I believe it's the largest in the country. We have 11 active patents, 5 patents pending. Dr. Bott will be talking about some of those in his presentation. The bottom line up front, like, what can innovation buy you? So we saved the region over $5 billion. And that's a number that came out of an ODU economic analysis that they recently completed. As I mentioned to you, there are 2 big regulatory drivers that we're dealing with for SSOs and Chesapeake Bay. And we did the math. And if every locality and HRSD, we all did our own thing and we didn't work together, the cost of compliance would have been over $8 billion. But we were able to come up with a very innovative integrated plan that a judge approved. So we converted our consent decree to an integrated plan. And we're able to do that for a little over $3 billion. And one of the reasons why is our SWIFT program has dual compliance benefits. And Charles will talk a little bit about SWIFT later. But what does this mean to our ratepayers? So ODU did the math, and they said we are saving, our ratepayer bills will be lower by 48% because of the innovative integrated plan that we were able to come up with. But that's not all. Some other ways we've been able to keep our ratepayer bills low. And this is our mantra, always researching ways to keep our ratepayer bills low. And Dr. Bott will talk about all the innovations on how we're trying to do that. And one of the things he'll be talking about is PD&A. We have the first plant in the world doing mainstream deammonification. But from a rate perspective, we save $1 million a year in O&M. But not only that, $100 million in CapEx. We worked with ODU to develop a low-cost PFAS method for GAC management. That is going to be our largest O&M cost for our SWIFT program. We can't wait 2 to 3 months to get PFAS samples back, so we developed this. It's a non-regulatory operational 30-minute test that's been super helpful to us. We closed a treatment plant and consolidated a plant that saved us $239 million NPV. And a lot of people have digester gas. They're always looking for different revenue sources. And where we lived on the risk profile is we worked a deal where $0 in CapEx, yet we're going to receive $400,000 to $500,000 in annual revenue. We just feel like from a regulatory environment, who knows how long RINs are going to be. Just recently, last month, the administration closed the offshore wind leases off Virginia. So Virginia has the largest offshore wind farm. Like, who knows what the regulatory environment is going to be? And so we did that deal last year. And this didn't really save us money, but it's an innovative example of how we're always trying to find that win-win. So we were looking for a location for a wet weather storage tank. There was a park nearby. We worked with that city and said, hey, if you give us that land, we'll build you a skate park. And so we built the skate park on top of this wet weather storage tank. Okay, so switching gears on to what our big idea is, we are creating this water technology focused innovation system. And the big vision is we want to be the Silicon Valley of water tech in Hampton Roads, with HRSD as the anchor for economic development. And so if you think about it, if you're a utility leader, it's really an optimization problem. So we have all of these great assets, we have all of this great R&D and patents, but what if we were more purposeful about generating economic development? And so that's what we're really doing. It's really an optimization problem. So here are some of our objectives with this innovation ecosystem. Similar to what Current is doing, we want to advance water technologies, but we also want to research ways to keep our ratepayer bills low, being efficient and resilient. And then doing things like this webinar, fostering collaboration and knowledge. And if we're very purposeful about that and we do it right, we can help drive economic development. And so AM Team is a startup out of Belgium. They do computational fluid dynamics, CFD modeling, and we're doing groundbreaking work with them, really cool stuff. But one of the co-founders, Wim, had this really cool blog post that went viral. And what it really talked about is how water utilities hold the key to innovation. And he published this water industry curve, and he talked about the chasm of a decade. And what happens there is like these startups have this really hard time of going from early adopter to early majority, and it takes about 10 years. And one of the things to note when Dr. Bott brings up a slide later in his presentation about one of our technologies called Indents that we've developed with DC Water, one of the things that you keep an eye on is how long did it take us to really have that first inflection point? It was about 6 to 7 years. And then it really wasn't until about 10 years that it really started to take off. And imagine that's HRSD, DC water. We're using this technology. It works. That's how long it took a utility with our brand name, our publish ability, and it still took that long to get that technology adopted. So one of the things that HRC is trying to do with this innovation ecosystem is like, how can reduce that chasm of a decade? Because you can have this brilliant idea, but that company couldn't survive this chasm, right? And so how can we help fix that? And that's how we think as a utility, we do hold the key. And that's one of the things why we're preaching to other utilities is like innovation is the key to affordability because we hold the key to innovation. And so that's really one of the underlining premises about this whole idea. So we've identified 4 economic development opportunities with our ecosystem. We can incubate or accelerate companies. We can attract companies. Maybe 6 months ago, we didn't have any, and now we have 3. EOS is formerly called Maya Water AI company. Tidewater Trident is commercializing one of our technologies called the Darbalizer. And the Radiance E-beam actually came out of the next opportunity is regional collaboration. So Jefferson Lab is a DOE particle accelerator laboratory, and we've been working with them. We published a paper with them on destroying 1,4-dioxane with their electron beam. But we were telling them, it was like all the challenges in the water space. And they're like, hey, we think our electron beam can destroy PFAS. And we'll talk about a little bit about that later. But how can we collaborate regionally with all the different assets in Hampton Roads to really create more economic development opportunities? We have NASA Langley's around the corner. Ferguson, they're the largest water company in the US that's trying to get more in the water wastewater space. Their global headquarters is in Hampton Roads. Their market cap is, I think, over 10 billion more than Xylem's. I'll talk about a cool partnership we've got with Waste Management. And then the idea you talked about, currents interested in circular water economy, the idea of industrial symbiosis and how we're trying to do that at one of our sites. And so this is a schematic of what our ecosystem looks like. It's very simple. Take an idea, test it at scale, and we've got investors tied into our ecosystem. So the idea could come from a university, it could come from a startup. We recently doing a partnership with Climate Haven, the university out of Yale and UConn are part of Climate Haven. We actually have one of the Yale startups that we work with, or the idea can come from HRSD. Then we test those technologies at scale. We just added Wintech Globus, a company out of South Korea, yesterday. It was a 3-way MOU between K-Water, which is the National Water Agency, Wintech Globus. They have this technology that uses superheated steam to regenerate GAC, and they have non-detect of PFAS in the condensate. And so that pilot is coming, should be here sometime this spring. So really excited about that. But then we also have 8 venture capital companies. We just added XPV, and then a number of industry partners. And we've got global partnerships with Singapore PUB, Aarhus Vand out of Denmark. So our ecosystem is alive and well. As an example, we introduced one of the venture capitals to one of the companies that were startups that we're working with, and they made an investment. I think they've made an investment in 2 of them now. And so that's kind of how our ecosystem is working. We're not asking for any money from anyone. It's really about relationships. So I want to talk a little bit about a startup case. And so we're working with 2 ocean alkalinity enhancement companies, Planetary. They won the $1 million X Prize last spring. And Crew Carbon, they've got $5 million in seed money. I think they've sold over $32 million in carbon credits. But bottom line is, from a business case perspective, we love this tech so much. We actually issued an RFP to expand this tech to more of our plants after seeing their pilots. We help mentor these companies. And so in a few weeks, we'll be able to announce which company that is. But that's like the best case scenario is working with a startup. We see so much value in their technology that we want to expand it to other plants. And so now, if you think about the ecosystem, we will provide that very important reference to help them scale because no water utility wants to be the first, right? But the more we can have utilities like HRSD that are willing to take a chance, pilot some of these technologies, it'll help these startups grow. Now I'll talk a little bit about a PFAS pilot we're working on with waste management. So as you know, one of the most cost-effective ways to deal with PFAS is get it at the source. And so we have landfill leachate coming to HRC. It's a landfill owned by Waste Management. So we are partnering with Waste Management on this study. So we know foam fractionization works. PFAS attaches to the foam, skims out. Okay, so now what do you do with that concentrate? And so they're going to be testing a number of different destruction technologies, one of them being the electron beam that Jefferson Labs is going to make, hopefully. But they're testing all of those different technologies that's listed here. And this is our opportunity for industrial symbiosis. So this is our largest treatment plant. It's a 54 MGD plant located in the city of Virginia Beach. Again, HRC is a regional entity. As such, we're tax exempt. This treatment plant's located in the city of Virginia Beach. So we have 300 acres of that vacant farmland that we purchased back in the 80s for buffer, right? Nobody wants to live right next to the wastewater plant for odors, for all kinds of issues. But then again, city of Virginia Beach gets no tax revenue. HRC gets no lease revenue. Well, if you think about it from an industrial symbiosis circular water economy perspective, what if you could put a data center there or some industry there that's community friendly that can use our digester gas, that can use our recycled water, right? And so I visited Denmark, and they have probably some of the best industrial symbioses in the world, and they've been doing it for a long time. So somebody's waste becomes somebody else's input, and they call it profitable sustainability. And so what we're trying to do is mimic that model, mimic that circular water economy concept, and look for opportunities like this. And I suspect there's lots of these opportunities around the country where you have wastewater plants that are, out in the middle of wherever that has tons of land, acres of land that could potentially be a great anchor for, a data center or something else. And with that, we're going to switch gears. I'm going to turn it over to Dr. Bott.
All right, thank you. So we have quite a few drivers for technology research and innovation. I'll start by saying not all of our plants have the land available that our Atlantic plant does that Jay just showed. Most of them are completely out of space. And so process intensification, along with decarbonization, are really some of our most important objectives. All of our treatment plants, except the Atlantic plant, in fact, are headed to TN of 4 milligram per liter and TP of 0.3. So more nutrient removal is certainly a factor. The impacts of SWIFT on nutrient removal, which I'll talk about in a second, is significant. Minimizing SWIFT capital and O&M costs, emerging treatment issues. The bottom line is, though, HRSD partners with our peer utilities and with universities to host graduate students working on the development of those technologies, and we partner with technology providers to deliver those technologies, ideally to us first, and then to everybody else. So SWIFT. So SWIFT is really indirect potable reuse by managed aquifer recharge, and this is resulting from a number of drivers, including reducing nutrient discharge, managing the groundwater supply in Eastern Virginia, potentially reducing or even reversing land subsidence, saltwater intrusion protection, and even economic development. So in the context of indirect and direct potable reuse, SWIFT is one of a number of projects around the world, and of course, potable reuse has become a very significant deal. HRSD started this work in about 2016, and we now have in place a demonstration facility since 2018, a 1 MGD facility, and the next phase is really full scale. So this is an update of what SWIFT is for us and what it will be, and that is 50 million gallons per day by 2029, 2 treatment plants, 116, 134. So this is adding advanced treatment and recharge wells. The first facility is commissioning right now. It's actually more than 80% complete now, very large project. And the second project is just getting going. The phase one is really a plant expansion, and then phase two is the SWIFT part. And that we've broken ground, but we're still at the 90% design level. It's a big design build project. The process flow diagram for the SWIFT Research Center and the first full-scale facility, which are quite similar, is shown here. And there's some interesting things to talk about, and I'll do that on the next slide. The first two facilities are quite similar. The second one has some changes, and those changes in the second one are really were driven by research. But this is very definitely carbon-based advanced treatment. So it's coagulation, flocculation, sedimentation, ozonation, biofiltration, granular activated carbon, UV disinfection, and recharge. And you'll see some things here, hopefully, that are causing some questions, and hopefully this answers some of that. So this is the sort of active R&D that is going on in the SWIFT world. So with respect to rapid mix, flocculation, sedimentation, really the objective is to intensify ozonation, maximize emerging contaminant removal, minimize bromate formation, and maximize disinfection. We've done a lot of work to get to our full-scale ozone system design. That work involved two PhD students from Virginia Tech. We've done a lot of work on biofiltration, trying to understand the impacts and effects on NDMA removal, adding propane as a co-substrate, even at this 1 mgd scale to enhance 1,4-dioxane removal, and demonstrating how robust the biofilters are to shock loads. From a GAC standpoint, this is where actually most of our work is happening right now. It's really in two pieces. One is minimizing GAC usage for PFAS removal, which is really driving GAC utilization right now, but also minimizing the cost of GAC. So Jay mentioned GAC reactivation. We're looking at microwave and superheated steam. Using ion exchange and novel adsorbents to polish after GAC, optimizing parallel gravity contactor operation, and so on. And then the last piece of work is really a big one, and this is honestly things we didn't know going into SWIFT and probably should have known more, and that's recharge well design and operation and hydraulics around recharge well. We have a lot of work going on in this area right now. So that's the SWIFT R&D. When we go back to wastewater R&D, really the name of the game these days is intensification, and I like this: do more with less in less. So do more flow, more capacity, better effluent quality, more nitrogen and phosphorus removal, reuse as SWIFT certainly is, with less chemicals, energy, labor, sensors, maybe even greenhouse gas emissions, in less concrete tank volume. The biggest cost by far is, whenever we decide we're going to build a new concrete tank for anything, it's $100 million just to get in the door. So the concrete tanks is really where the money gets big these days. So one of the technologies that we're very proud of that now is quite a few years old is indents, and I'll just give an overview of this. So this is now more than 140 installations globally across 40 countries, including some big ones in the U.S. And this in the U.S. has been commercialized with World Waterworks. This is number one. This is about 10 years ago in our James River plant. And those of you who recognize indents will not recognize these cyclones, and that's because these cyclones that we first installed at James River plant didn't really work. And when that happened, we set about on a program to understand how to size and select cyclones, and we had built this big test rack and tried to get our hands on every cyclone we could, and slowly figured out what made sense in terms of the cyclone to choose. And this is what that cyclone now looks like. And it is basically deployed as a selective wasting approach to waste the less dense, slower settling material and retain the heaviest material. It can also be applied typically in smaller plants in this mechanism and sort of more of a hydraulic wasting approach. And so this technology has really grown. Again, this was developed, I guess, jointly by HRSD and DC Water, but it's grown pretty significantly. And this is our newest installation at our Army base plant. This is what the equipment package looks like now. We just put this in, and this plant in particular has wintertime Microthrix parvicella problems. It's our only BNR plant that has that problem. We have no idea why, but this is our solution for that problem. And we're expecting a much better winter and spring from a settling standpoint of this plant. So as George mentioned at the beginning, one of the things we've been working on now for almost 15 years is shortcut nitrogen removal. We have a lot of work going on to upgrade our treatment plants for better and better nitrogen removal and more nitrogen removal, basically moving them all to 3 or 4 milligram per liter TN. And so doing nitrogen removal in a way that makes more sense is really the goal. Nitrite shunt is one way of doing this, and I think probably most of you are aware that we know how to grow AOB and not NOB in the side stream part of the plant, centrate treatment from anaerobically digested solids that's warm and high in ammonia. But I would argue that nobody has figured out how to do this in the main part of the plant reliably yet, and reliably being the key there. The second piece of this is, of course, Animox, that if we can figure out how not to grow NOB but grow AOB, and we combine that with Animox, then we get partial nitritation Animox, and this is really the holy grail. This is what everybody wants. I mean, again, we know how to do this in the side stream part of the plant. The key is doing it in the main part of the plant. So the main challenge is sufficient retention of Animox while allowing SRT pressure on other organisms. We know how to do this now. Animox are not the problem. We have to provide an appropriate place for Animox that accommodates their slow growth rate, and we know that biofilms do that really well now. But number 2 here in the main part of the plant is a real challenge. So again, we know how to do this in the side stream for anaerobically digested solids. It's both warm and high in ammonia, and that makes that NOB out selection work really well. HRSD was the first to do this in the US, or in North America, I guess. In 2012, we converted a tank that was available here to Demon, a side stream P&A process. And actually in 2026, we'll be converting it to a little bit different version of that called Deanna, which is basically a moving bed biofilm reactor process. So for our plants with anaerobic digestion and the need for nitrogen removal, we're basically now covered with respect to side stream deammonification. We have it at all 3 of them, York River, James River, and Nansemond. The last one actually we just installed right now and are in the process of starting it up. So side stream P&A, no problem. Mainstream, there's really not that much happening, and there's some publications, but really probably it's not clear exactly that these plants are achieving a lot of nitrogen removal through P&A, and the real challenge is NOB out selection. So if we go back to our schematic here, while we would like to do P&A, and this is really the goal, what we discovered some years ago is that while P&A is really hard, pDNA just works. And it is a compromise. And, I think we really didn't get serious about this because of understanding this compromise. But as we discovered how well this works and that it gets Animox in the plant, and we do get some meaningful benefits, then yeah, we are now doing this. And the word detour has been used to describe this, and this is a nice, interesting play on words from Heidi de Cliplier at DC Water. Taking a detour to achieve a shortcut is what we're quite proud of, and that resulted in this whole thing getting branded as detour. So at HRSD, we've been working on this for quite a while. It goes back to 2012 and pilot work. Really done in the context of AD at the time, and really mostly focused on P&A. We did a filter pilot in 2020 to 2021, and since then we've been working on MBBR and IFAS. This is the original pilot work, which was actually done in a polishing MBBR and was done in this reactor. And there were a number of graduate students that went through this pilot facility from quite a few different universities, and a picture of some of those various teams over the years. The new pilot facility looks like this, and is focused on MBBR and IFAS and another group of graduate students, although I need an updated picture because all of these students now have moved on and we have a new batch. So with respect to what we've done, HRSD and DC Water. So we've all been sort of working on this together with various universities for a long time now, but we really didn't get serious until 2018. And when we realized then that this MBBR was working quite well doing PDNA, we decided immediately to go full scale at our York River treatment plant in a filter, although we had never piloted that. And it worked quite well. And since then, we've been doing MBBR and IFAS, and I'll talk about what that looks like full scale. But before I do that, this is what we know how to do. So from a process standpoint, we know how to do PDNA in a polishing type process, an MBBR or a deep bed filter or a bath. We know how to do it there, and we know how to do it in the form of IFAS in a second anoxic zone. From a process standpoint, this is not a challenge. From an engineering standpoint, it's very definitely a challenge. And that's really mostly related to trying to get IFAS retrofitted into existing aeration tanks that maybe don't have the head loss to readily allow screens to be installed to retain that media. One of the things that goes with this, and both a benefit and a challenge, is the need for AVN control. So what PDNA requires then is that we feed these zones properly. And that happens with AVN control. So we don't care what the ammonia is going into this anammox zone, as long as there's enough anammox activity to remove that ammonia. The key then is the ratio of ammonia to NOx. And if we don't get that ratio right, based on the PDN efficiency that we're seeing in these PDNA zones, then we don't get good low effluent total nitrogen. So controlling AVN is really the challenge here, and that can be done by manipulating DO, aeration time, step feeding, and it's really just a bump up in complexity from what we already do, which is ammonia-based aeration control. One of the benefits, though, if we think about this, is that PDNA becomes a really significant intensification technology. So what do I mean by intensification? I mean that it's driving the size of these aeration tanks and clarifiers, which I already pointed out is where the big money is. And so how does it do that? Well, we're not reliant on maintaining an aerobic SRT sufficient to drive the ammonia at the end of the aerobic zone to very low concentrations in the wintertime, right? That's what's determining the volume of this whole thing. Now we're reliant on this anammox process or PDNA process to remove some of the ammonia downstream, and we can let 3 or 4 or 5 or even 8 milligram per liter of ammonia slip out of this aerobic zone to the PDNA zone and rely on anammox to remove it. And that is a huge intensification benefit. So let's just kind of review. This is very much a state of lots of argument right now in the industry, but this is my very much my opinion on this, and very, very, very definitely up for argument. But this is what I think of the important concepts from intensification standpoint. One is managing mixed liquor settling limitations. So we think granular sludge or indents or Narita, or just remove the need to sell it all together with a membrane bioreactor. Maybe we divert carbon and decrease the COD and TSS load. 2, selectively retain slow-growing nitrifiers, which allows a suspended aerobic SRT to decrease. And there are lots of options for doing this: IFAS, MBBR, MABR, selective wasting, and so on. And then the last one is move the ammonia removal out of the aerobic zone, move it downstream, and this is how post PDNA becomes an intensification technology, and MABR may be much the same. So we, as I said, we went full scale at York River in our D9 filters in 2018, and that resulted in a significant savings in chemical and energy. This is our York River plant. It was an ideal plant to do this. We use a lot of methanol, caustic, and ferric because the existing system, for some old reasons, was a fully aerobic, fully nitrifying activated sludge process, followed by full D9 filters. We converted those filters to PDNA filters and actually converted the upstream process without any additional concrete to a pretty radical intermittent aeration with intermittent step feeding. And that resulted in both this aerobic SRT decrease, which allowed carving out anaerobic and anoxic zones, and a big savings in methanol. But we also eliminated caustic addition and nearly eliminated ferric addition, because now this plant does BioP as well. And we realized that while this worked and it took about a year to get going at full scale, we really didn't learn everything we needed to know about about pDNA in a deep bed filter. And so we partnered with Xylem to bring in their Eliminite pilot system and partnered with DC Water. And this is the graduate student who actually worked at this pilot at our York River treatment plant. And after with a year of piloting, the results were that there's really no compromise in the full-scale design of a filter to accommodate pDNA, meaning that if we design a filter to do full denitrification, it can readily be adapted and converted to do pDNA. There's no reason to switch to glycerol based on the cost comparison with methanol. That was one of the questions. Glycerol is known to do better PDN than methanol, but it doesn't warrant, based on the cost difference, a switch to glycerol in a filter. And the filters were never Animox biomass limited. There was a huge excess of Animox activity grown up in these filters over time, and we see the same thing full scale. So while we might be able to load the filter with up to maybe 8 milligram per liter of ammonia, the filter has the capacity to remove as much as 30 milligram per liter. And that's very important for getting through the winter, meaning that the temperatures of our wastewater cool off faster than we can expect Animox to grow up. From an IFAS and MBBR standpoint, we've learned a lot as well, that it takes about 2 to 3 months under warm temperature conditions to establish Animox without any Animox seeding. And so we don't call it summer anymore. We call it Animox growing season here. And we're actively waiting for summer right now to grow Animox again. Animox and nitrite concentrations for establishing Animox are low. Ammonia and nitrite concentrations for establishing Animox are low, meaning we only need about 1 milligram of ammonia and nitrite in the bulk to do that. And the key for partial denitrification is very carefully controlling the nitrate residual. I mentioned before, good AVN control is really critical. So at James River plant, we did this. We went straight from pilot to full scale in a very small zone, and this is now a small second anoxic zone that we carved out at this plant that already had aerobic IFAS and are now doing pDNA by IFAS in this whole plant. And we've got Animox now grown up in almost all of these tanks now at a pretty high rate that's very similar to what we saw in the pilot, sufficient to remove between 2 and 4 milligram per liter of ammonia in that tank. The next plant is Nansemond, and we're actively converting the first cell of the second anoxic zone at this plant to pDNA by IFAS. This tank number 6 here was supposed to have started up in January 2025. We had a lot of problems with the IFAS part of that. We've made some design changes and built them, and are in the process of putting that tank back in service now. So that's pretty exciting. This is a much larger plant. This plant is being expanded to 50 MGD. So yeah, much bigger application here. As I mentioned, one of the challenges here is AVN control, and we're relying on our understanding of operating most of our plants in ABAC, where we position an ammonia sensor at the end of the aerobic zone and use that with a PI loop up to determine the appropriate DO set points that meet that ammonia set point here at the end of the aerobic zone. We've done this and we know this, and it works, but it's most definitely not perfect. And when we think about converting this to AVN, it needs to be definitely better. One of the issues is sensors, and about 8 years ago, we started a program to develop our own online colorimetric analyzer. We've done this. We have about 25 of these now deployed. So we've designed this system, we build them, we fabricate them, and we've installed them at our treatment plant. And JARBA came from a guy named Josh and a guy named JARBA Lizer. And this online analyzer does ammonia, nitrate, nitrite, and orthophosphate, real time in the field. There's some interesting innovations here, and we've now sort of gotten this relatively mature, and we like it. And our demand for them, even at our own treatment plants, is more than we can meet. Josh has been replaced by Shelby, but we're still continuing to do this. But we're also now looking to commercialize this and just starting that process right now. The other thing we're thinking about a lot is the controls to do AVN, and we've done a number of different approaches. One is just adjusting for the changes in influent flow rate, and that's been done at James River plant. That sounds quite simple, but it's not. It requires a model that predicts what the DO should be based on the influent flow rate, and it's not trivial to get that model. And it's also not a model that's consistent year long. Ali Gagnon has done something something a little more sophisticated. And then Jeff Sparks at our Nansman plant created a hybrid mechanistic and data or machine learning model with an added ammonia sensor running on a digital twin, a Sumo-based digital twin at our Nansman plant. And that's worked quite well. And as a result of that, Jeff Sparks is now our director of digital water. And we have a sort of brand new department that's focused on harnessing data and models to optimize wastewater operations and lower cost and really driving innovation toward resilient and efficient wastewater systems. So in a very short time, in about 2 years, we've developed a whole digital water department with 3 engineering staff, one focused on GIS and spatial type topics, one focused on treatment plants, and one focused on hydraulics and pumps and pipes and the interceptor and collection system. We've gone after very specific talent here with outside entities. So reinforcement learning from a guy named Henry Cole at HDR. We partnered with Maya Water for their agentic AI solution. Peter Van Rallingen is actually tied in closely with this group, and we have another PhD student working as well here. The digital water group is really focused on problem solving. So the low-hanging fruit is the key to this group, meaning we've identified more than a dozen problems, and the objective is to use the tools that we have available now internally with our own staff to solve those problems. And that list of problems includes both treatment plant problems, associated with ABAC and AVN, flow forecasting and equalization tank management, force main pressure forecasting, break detection. So these are real problems that we think we can use the AI and machine learning and data analytics tools that we have available now to solve them. And we've done it, and we've deployed these in a lot of cases. One of the things that seems to be the case is it's easy to get to 80% of the solution, but it's really hard to get something actually built, deployed, and working. And so that's the objective, to solve these problems and then learn from doing that so that we can go broader and deeper with other problems. We've created the foundations of a data pipeline, one behind the firewall of our plant control systems, plant and collection system control systems that's focused on control, and then one outside of the firewall that's focused on guidance and dashboarding. And operationalizing, as I mentioned, is important. This is that ABAC controller that Jeff developed. We've got some generative AI and agentic AI applications coming in collaboration with Maya Water. And we've even started some work on wearables that would provide information to operators and mechanics in the field. And robotics as well, focused on providing monitoring around a treatment plant that takes some load off of our staff. So one of the interesting, really interesting observations that we've made recently is that there's a lot of tiptoeing around the use of AI tools and the development of those tools such that people lose their jobs. And what we have done is kind of turn that on its head, and we've said, well, we're not going to tiptoe that. We're just going to eliminate shift work. And so what we've established as a goal for our digital water department is, even at our largest treatment plants, to eliminate shift work, meaning our goal is to staff our treatment plants 5 days a week, 8 to 12 hours per day, and eliminate night and weekend work. We can hire really good operators, but nobody likes to work shift, and that's one of the most significant reasons we lose them. And so, combining problem solving and things we can do within our R&D department and also within our digital water department is an important part of that, and that's where that imaging work comes in. One of our newest areas is really focused on low DO, understanding mechanistically acclimation of autotrophs and heterotrophs and to low DO. And it turns out that this is where our work on BioP fits in, and where we're working a lot to make BioP better even in the summertime. It's really focused now on low DO. And I'll just mention, it's not all complicated. As we go to low DO, we realize we need to separate mixing and aeration in our aerobic zones. And so along comes Minion. Mike Parsons developed this large bubble mixer. It's really just an inverted siphon, which you see here. We developed this some years ago. We now have a lot of them installed at our treatment plants, and for basically no energy and very low capital cost, we can mix aerobic zones or anything else really that needs mixing, and separate aeration and mixing and allow aerators and diffusers to turn off and keep mixed liquor mixed. We commercialized this as well. There was a lot of demand for it, and we hadn't planned to do that. We were just building them and installing them ourselves, but based on the demand and people wanting them, we commercialized this, and now Waterworks is selling these Minion mixers, and they even have partnered with, or we partnered with AM Team to do some CFD modeling of the Minion mixer. And again, this is using air. This is the commercially available Minion mixer, which is made from welded HDPE, not PVC fittings, but it looks a little more robust and a little more formal. But basically, it's using low pressure air right off the same air header that the diffusers are using. Air continuously fills this reservoir and it periodically burps out. And yeah, that's how we mix our tanks now. So I'll end with a quick overview of the side stream part of our Nansemond plant. And I know that's an odd thing to talk about here at the end, but I think there's some interesting things to talk about. So for the last, since 2010, we've had in place at our Nansemond plant the Astera struvite recovery process. And when that was originally installed, it uses magnesium chloride and sodium hydroxide. This plant has anaerobic digesters, but you'll notice there's no side stream nitrogen removal. If you remember back, I just mentioned that we solved that problem. We added side stream PNA, and that's not on this diagram because I'm getting ready to show you what the Nansemond side stream system looks like, or is in the process of looking like right now. It's under construction, but this is what the side stream part of that plant becomes. And wow, it's complicated. And I hadn't really realized how complicated this system is until now. But there's some interesting pieces in this complication. And the point of this is that while this is really complicated, this is what it takes in order to achieve all the things we want. So first of all, we've installed Greasezilla. We have a lot of truck delivered grease waste coming into our treatment plants. This is one of 3 facilities that receive grease. At this facility, we installed a process called Greasezilla, where we convert that to a low quality fuel oil that's used on ships. It's bunker fuel. And then the residuals of that go into the digester. We've added WAS strip that results in more phosphorus stripping and therefore more struvite production. And there's some separate pre-dewatering associated with that to intensify these anaerobic digesters. And we've installed side stream PNA MBBR that's not really branded because it's our own design here. But when you put all that together, what that means is now the struvite recovery facility is alkalinity short. We now no longer have sufficient alkalinity to make it cost effective to operate, but we have the potential to generate a bunch of struvite. So we had to set about figuring out how to, if we're going to make it cost effective, no longer use magnesium chloride and sodium hydroxide, but transition this facility to magnesium oxide. And it took about a year and a half of pilot testing on one of the full-scale reactors to really figure out how to do this. And now we're in construction for a dry magnesium oxide system with a slaker to feed that system. So I'll conclude with that, really what we're doing here is leveraging our infrastructure and our expertise and our R&D group here for economic development opportunities and community impacts and building partnerships and collaboration. But we're also using our applied R&D to manage the risk of deploying new technology. Don't wait for others to bring innovations here. Utilities, our peer utilities are not our competitors, so we work to collaborate, and we work to get universities, consultants, and tech providers involved. But in the end, we try hard to drive our own goals. And what's next? So PNA remains the future goal. We're pivoting back to PNA now from a process research standpoint, although we still have engineering work to do to figure out PDNA by IFAS. And what we think is that PDNA is really the path to make PNA possible. And we've got some indication that seems to be right. Using wastewater carbon as efficiently as possible. And we have one plant where we're doing that. As I mentioned, intermittent step feed with intermittent aeration. Low DO, we're headed there whether we like it or not. If we want to do all these other things, these processes are going to be operating at low DO. And we think that might be really the key for making BioP really reliable. And sensors and controls are becoming more and more important, and generative AI tools and all sorts of interesting tools and methods are coming quick, and we've responded with our new digital water department. So that's it. Thank you for your attention, and we can take some questions now, I guess.
Awesome. Thank you, Jay and Charles, so much for your presentation. This is really, really fantastic to see, um, just seeing how vast your network and your ecosystem is, and just getting to scratch the surface and all of the great innovation that you all are working on is really, really fantastic. So yes, we do have a couple questions in the queue already, but if anyone else has questions, feel free to submit them. We might not have time to get. We can see what we can get to. So first, have a question about, so thinking about all the stakeholders that are impacted by the just general operation of your sanitary district, thinking about like environmental regulations and things of that nature and all of the risk associated with just like maintaining the status quo. How do you convince like ratepayers and politicians and all of those stakeholders that the risk associated with innovation is worth it?
I think we were lucky in the sense that we have already demonstrated ROI. So to our
Mhm.
commission, um, that's why our R&D group has grown to the size that it has. Is we didn't list all the wins, obviously, in terms of how important our R&D group is to keeping our rates low. I mean, I remember when Charles started, I think 2009, right, Charles? Even though we had to lower um, nitrogen and phosphorus concentrations, our power and chemical cost remained constant throughout that entire time. Yet we were standing up all of these new plants, and so I think for us, it was we were able to show quick wins, which is almost to the point of, well, why are we one of the first in the country to stand up a group focused on AI? Well, because they are already showing ROI, and one of the things that Dr. Bott was talking about is just focusing on the low hanging fruit. And so, I think because we've already had a track record of success, it's been much easier for us to just continue and just continue to ramp that up. So, as an example, yesterday we did K Water and Wintech Globus came in for an MOU. We had three of our commissioners there that just loved it, just loved to see that we're building now global collaborations and partnerships with different innovations that other people have. That it's not our innovation, it's other innovations that people have. But at the end of the day, it could potentially save us a lot of money in the long run. So I think
Mm.
continuing to demonstrate ROI and again, our mantra that resonates with our ratepayers, and we've tested this, is we're always researching ways to keep our ratepayer bills low. And in my mind, that should be an expectation if you're a ratepayer.
Gotcha. Great. Um, Perfect. And then kind of touching on that AI kind of focused group that you mentioned, and that Charles you were talking about. Um, what do you contribute to, in addition to just like your track record, how do you contribute, or how do you frame like your success and your ability to stand that up so quickly? One person that submitted a question proposed if maybe like not having to work with an IT department that's like focused on like all city operations, like you being an independent sanitation district, just kind of postulating if that was a factor that supported that quick standing up, or if there are any other factors that you think contributed to that.
I mean, there's no question being an independent district helps in that regard. We have a we have a very collaborative IT department though, and that certainly helps. But I think some of the other factors involved here was that Jeff started as a mature engineer having a lot of experience and wanted to do a PhD, and his PhD was tied to developing that new ABAC controller. And he did it and deployed it at the treatment plant where he was the responsible process engineer at the same time. So that was a real that he just figured it all out and did it and deployed it and then had an opportunity to test it I mean, it was sort of obvious to all of us when we saw that happen that this is something that needs to stay and this is something that needs to grow and that he's the right person to do that. So we were very fortunate and that it just worked out that way. But we also worked to we had, for example, when he hired two of the engineering staff, we had two applicants, both with really good skills. We'd intended to hire one, but they both brought such interesting and good skills. We decided we just hire both of them, and that really took off because now we have expertise with Jeff on both the treatment side and on the interceptor collection side. So.
And I do think that it's an interesting question because it really goes back to one of HRSD's fundamental policies is investing in our people. So, for example, HRSD has a policy where we pay 100% for your school. So they paid 100% for my MBA. We paid for Dr. Sparts to get his PhD. And so there are so many stories within our organization where we've invested in them, they've gotten their education, and that return on that investment has just been exponential. And so it really goes back to, again, investing in your people.
Yeah, I'm really glad that you touched on that because my first follow-up question is going to be, it sounds like, talent recruitment and then development sounds like to be a really big contributing factor to like the success of your innovation programs.
It's all about the people.
Oh yeah. Well, fantastic. So do want to be respectful of everyone's time. This was really, really great. I'm sure we could talk all day about all of the great work that you're doing. But I do want to just give a quick preview to our attendees of what is coming next for the Third Coast Water Seminar Series. So I'll just share my screen really quickly. So this is a monthly series. So our next seminar will be on February 4th at 11 a.m. This will also be a virtual seminar. We will be hearing from Dr. Jason He on nutrient recovery from wastewater sludge. So we encourage everyone to attend that one as well, to share broadly. And then if you know someone who would really appreciate learning about what we discussed today, we will also be posting a recording of today's seminar on our YouTube page. So you can find links to that on Current's website as well. But yeah, without further ado, we will thank everyone for their attendance. Thank you, Jay and Charles, for again, just like a really fantastic presentation today and discussion at the end. And we hope to see you all in February. Take care.
Thank you.